Okay, so where we left off was with the force of friction. And I was just saying at the end of the other video that the more the two surfaces are pushed together, the more friction there's going to be. Right? If you could imagine like any surface that has friction, if we magnify it, might look like this. And so if whatever is resting on the surface is resting on top of some of the bumps and I'm pulling it, then as I pull it, it can just kind of glide over the top of the bumps. Yeah, it feels the bumps a bit, but it's not really getting too much into the bumps. But now, if for whatever reason, like if it's my toboggan and someone else sits on it with me, now I'm pushed more into the bumps. So now the object is sitting deeper in here. And because of that, it takes more force to pull it. Okay? And so we say the more tightly the two surfaces are pushed together, the more friction there's going to be. What pushes the two surfaces together is our good friend, our good buddy, the normal force. So we say that the force of friction is directly proportional to the normal force, and I'm hoping you've seen that symbol before. That little fish symbol means directly proportional to. In other words, friction and Fn, if you were to divide them, directly proportional means one doubles, the other doubles. If one triples, the other triples. They change in the same way. And so if you were to do FFR divided by Fn, it means it's equal to some constant. And this constant is what we call the coefficient of friction. Okay? And the coefficient of friction is constant for a given surface. In other words, if I have my toboggan on snow, on a particular thing of snow, then the coefficient of that snow would be given. But if I then took my toboggan and put it on gravel, then the coefficient of friction is going to be different because the gravel has a different texture than the snow does. Okay, so constant for a given surface, but changes from one surface to another. And the symbol for this coefficient is the Greek letter mu. Now, and it's spelled mu. And it's a U with a tail, and you've already seen it. It's the micro when we did the conversions, right? The metric conversions. So it's mu. And mu doesn't have any units because look, it's friction divided by Fn is equal to mu. Well, friction is in newtons because it's a force, and the normal force is in newtons because it's a force, so it's going to be newtons over newtons, so mu is not going to have any units. And actually, mu has a range of values, and that range is usually between 0 and 1. There's a chart in your textbook that has values for mu. It's on page 140, and the very first one, it says it's between, the value is bigger than 1. It's the only spot I've ever seen a mu bigger than 1. So usually if you're calculating mu and you get it to be bigger than 1, it usually means you've screwed up. This equation then, we write it as FFR is equal to mu Fn. Okay? Now, in high school physics, force is always a capital F. But when you get to university, you'll discover that a lot of profs write friction as a script F. And you'll discover that a lot of profs write the normal force as a capital N. And so this equation becomes what hopefully you've already figured out. It becomes the fun equation. It's a lot of fun. So you'll never forget it because it just spells fun. It's also on a clock in my room, as one of my former students made a clock for me with it. Okay, so physics is fun, and so is this equation. All right, so that's our equation. Now back to the coefficient again for a minute. I said as a range of values between 0 and 1. When do you think the surface is smooth? When it's closer to 0 or closer to 1? You should be able to tell by looking at the equation. The bigger the mu is, then the bigger mu Fn is going to be and the bigger friction's going to be. So the closer mu is to 1, the rougher the surface. And the closer mu is to 0, the smoother. Okay? Now just a couple other little things about friction. So this is the equation we're going to use to find friction. The couple other little things is that there are 3 different types of friction. It's light glare here from my window. So the first type is called static friction. And static friction is friction between objects that are at rest with respect to each other. So this, and with respect to each other, means the whole thing might move. This box might be sitting on the back of a truck, and the box might have your grandmother's fine china in it, and your friend might be driving this truck, and you might say to your friend, okay, thanks for taking this across the river for my grandmother. Just make sure the box doesn't move while you're doing it. And your friend's like, I'm taking it across the river, but the box isn't supposed to move. But what you're talking about is the box isn't supposed to move with respect to the truck. Make sure that the box isn't sliding around the back of the truck. And it won't, as long as the static friction between the back of the truck and the box is big enough. Okay, so static friction then is the friction that exists between objects that are at rest with respect to each other. Remember, with respect to is WRT, each other. The light. Honest, I'm writing ever there. With respect to each other. Okay? It does obey the equation FFR is equal to mu Fn, and it has special values for FFR, so you can look them up on a chart. They're the static coefficient of friction. They are always bigger than the kinetic coefficients of friction. It's always harder to get something to move than to start something moving than it is to keep it moving. Static friction varies up to a maximum amount. And that maximum amount is what we find when we calculate static friction using this equation. This is the maximum it could be. Okay, but it doesn't have to go that big. Now, what I mean by that is imagine that I have a box here and I'm pushing with a force of, 10 newtons. And you do FFR equals mu Fn, and you solve that the static friction is 20 newtons. Well, there's no way that static friction is going to push on this box with 20 newtons if I'm pushing with 10, because if it does, it means the box is going to slide in the opposite direction I'm pushing. Okay, so imagine the box is just sitting here on the floor. I come along and I push with the force of 10 newtons and the box slides in the other direction. Like, what kind of a loser am I going to look like? And friction will never make something move. It will always oppose motion. So this 20 newtons that we find when we do mu Fn, and I'm just making up the 20 right now to give you an example, but it's the maximum value that can exist. So if I push with 10 newtons, then friction will push back with 10 and the box will stay stationary. If I push with 15, friction will push back with 15. 20 static friction will push back, 18 static friction will push back with 18. It's only when I hit 20 newtons that the box will begin to move. Once I match this maximum value of static friction, then the box begins to move. And as soon as the box begins to move, then we switch to what's called kinetic friction, the second type. Okay, and kinetic friction is friction of motion. Okay, so it's the friction between two objects that are moving with respect to each other. It also obeys FFR equals mu Fn, but its mu's are different. They're kinetics, where these guys are statics. So the light just keeps shifting on me. So when you look at your table, on page 140, and the light is really bad on it right now, you will see two columns, one for static and one for kinetic, for different surfaces. You will also see that the static one is always bigger. Why is it always